Welcome to our comprehensive masterclass on quality control and quality assurance, the backbone of manufacturing excellence in modern India. Today we'll explore how QC and QA have evolved from simple inspection processes to sophisticated theory-driven disciplines that define world-class enterprises. Quality control is a multi-dimensional, theory-rooted discipline that operates as the first and last line of defense in an organization's pursuit of excellence. QC leverages systematic procedures, statistical science, and behavioral rigor to ensure every output meets or exceeds both customer and regulatory requirements. Systems theory views an organization as an interconnected system, where process, input, and output are managed through feedback and corrective actions. Deming's PDCA cycle, Plan, Do, Check, Act, provides the foundational framework for continuous improvement and learning in quality management. Duran's quality trilogy, quality planning, quality control, and quality improvement, creates a self-reinforcing loop of defect prevention and process optimization. Specification setting involves defining measurable quality parameters, tolerances, and acceptance criteria aligned to customer and legal standards. Inspection and testing requires layered checks using calibrated, validated instruments at raw material, in-process, and finished goods stages. Advanced QC integrates inline sensors and AI-enabled vision systems for zero-defect ambitions through real-time process monitoring. Real-time surveillance using statistical process control charts, alarms, and feedback systems triggers prompt analysis and containment when deviations occur. Root cause analysis employs systematic methodologies, fishbone diagrams, Pareto analysis, 5 whys, and FMEA to identify failure sources. These analytical tools systematically prevent recurrence through robust corrective action and continuous improvement initiatives. Data is the quantitative and qualitative substrate from which all quality control insights, interventions, and optimizations emerge. Measurement system design requires selection and validation of instruments, calibration schedules, and protocols that align with process capability. Automated and sensor-based data acquisition integrates IoT sensors, machine vision, and inline metrology for high-frequency data capture. Real-time process data from SCADA, MES, and IIoT platforms provide instant feedback loops for process stability and predictive analytics. Statistical measures of central tendency, mean, median, and mode distill vast measurements into meaningful values representing typical process performance. In high-precision sectors like pharmaceuticals, the mean is tracked at every stage and compared against process targets and specification limits. Variation is universal in all production processes. No two outputs are ever truly identical. Understanding variation types is fundamental to process stability. The distinction between chance and assignable causes of variation is not just technical, but strategic for predictive quality management. Common cause variation represents intrinsic, random fluctuations from the inherent design of the system, machine vibration, temperature drift, routine wear. These variations form stable, predictable patterns described by normal distribution within control limits, indicating the process is in statistical control. Special cause variation represents non-random deviations from specific, identifiable sources. Equipment malfunction, defective materials, human error. When special causes are detected, immediate root cause analysis, output quarantine, and corrective action prevent defective products from reaching customers. Process capability statistically assesses how well a process can consistently produce output meeting specified customer or regulatory requirements. CP measures process spread relative to specification limits, while CPK accounts for both spread and centering, providing realistic performance assessment. Indian automotive suppliers regularly conduct capability studies on critical dimensions, presenting CP and CPK results to global OEM customers. A CPK below 1.33 on safety-critical parts triggers immediate cross-functional reviews, while strong capability enables fast-track approval and expanded business. Historically, quality management relied on inspection-based quality control, a reactive, post-facto process focused on defect detection after production. This reactive approach incurred substantial costs related to material scrap, inefficient labor utilization, and production time loss without addressing root causes. Quality assurance represents a proactive, process-centric philosophy oriented around defect prevention rather than detection. QA designs, implements, and manages the entire production system to integrate quality at every stage, making prevention more economical than correction. Philip Crosby's right first time doctrine demonstrates that quality is free. The costs of poor quality consistently exceed prevention investments. The price of non-conformance, rework, scrap, warranty claims, customer dissatisfaction exceeds investment in robust first-time right processes. Quality planning establishes the strategic foundation, translating customer requirements and regulatory mandates into specific, measurable technical specifications. Key outputs include comprehensive validation master plans and formal risk registers such as failure modes and effects analysis. Quality system infrastructure provides the procedural framework, controlled document hierarchy, QMS software, equipment calibration, and change control. This creates a controlled, consistent, and auditable system of procedures ensuring operational excellence and regulatory compliance. Operational quality assurance embeds quality principles directly into production through real-time process verification and immediate deviation response. Operators are empowered to flag process deviations instantaneously, ensuring verified real-time adherence to established procedures. ISO 9001 is the internationally recognized standard specifying quality management system requirements, certifying organizational quality management capability. ISO 9001 certifies that organizations have established, documented, and maintained robust systems for consistently delivering quality products and services. The standard's architecture is founded upon the Plan, Do, Check, Act cycle, providing iterative methodology for continuous improvement. Plan establishes objectives and resources, Do implements processes, Check monitors performance, Act improves based on evaluation results. Indian SMEs leverage the government's Z scheme to accelerate their quality journey, enhancing global competitiveness through quality standards adoption. Z provides significant financial subsidies for consultancy, training, and certification costs, making world-class quality systems accessible to MSMEs. The Bureau of Indian Standards grants the ISI mark, India's official mark of conformity representing trusted quality and safety for consumers. Product certification attests that specific products conform to required safety and performance standards, providing direct consumer assurance. High-risk items like gas cylinders and safety helmets require stringent Scheme 1 certification with comprehensive factory audits and extensive testing. Medium-risk electronic products use the compulsory registration scheme, a streamlined process based on valid test reports from recognized laboratories. The licensing process begins with digital dossier creation through EBIS portal, including quality management system manual and detailed process flowcharts. Factory compliance audits verify manufacturers possess requisite infrastructure and systems to consistently produce conforming goods. Third-party validation involves independent laboratory testing of sealed samples, with official test reports submitted directly to BIS. Statistical Quality Control applies statistical methods to monitor, control, and improve processes through objective, data-driven decisions. SQC distinguishes between common cause variation, natural process noise, and special cause variation from specific assignable sources. Shewart's 3 Sigma logic places control limits at 0.3 standard deviations, where 99.73% of normal data naturally falls within limits. The central limit theorem enables valid application of normal distribution theory through rational subgrouping across diverse industrial processes. Advanced SQC utilizes AI-assisted pattern recognition to detect subtle, non-random patterns, providing early warnings before non-conformance occurs. Acceptance sampling employs statistical principles to infer lot quality from small samples, when 100% inspection is economically infeasible. Indian pharmaceutical sector demonstrates sophisticated QA implementation with 21 CFR Part 11 compliant digital documentation and AI-powered analysis. Automated real-time release systems enable continuous compliance with stringent US FDA and EMA requirements, supporting India's global pharmaceutical leadership. Dixon Technologies exemplifies advanced QC with AI-driven inline camera inspection, generating high-resolution, real-time dimensional and defect data. Cloud dashboards empower plant managers and remote quality experts to proactively identify bottlenecks and benchmark performance across multiple sites. Indian food processing demonstrates rapid quality deviation response using AI-augmented control charts and 8D problem-solving methodology. Swift containment, corrective action, and process monitoring intensification prevent potentially catastrophic recalls, protecting brand reputation. The future of quality management integrates Industry 4.0 technologies, IoT, AI, machine learning, and autonomous systems for predictive quality control. Predictive analytics enable organizations to prevent quality issues before they occur, moving from reactive to proactive to predictive quality management. Digital twin technology enables virtual quality optimization, allowing organizations to test and refine processes before physical implementation. Blockchain technology ensures immutable quality records and complete traceability throughout global supply chains. Future quality management integrates sustainability, social responsibility, and environmental stewardship with traditional quality excellence. Quality systems evolve to support circular economy principles, ensuring excellence while minimizing environmental impact. We've journeyed through the evolution from basic quality control to comprehensive quality assurance, exploring theoretical foundations and practical applications. Quality management has transformed from inspection-based detection to prevention-focused, data-driven, systematic excellence. Successful implementation requires systematic approach, from statistical foundations through ISO certification to advanced digital integration. The ultimate goal is creating a culture where quality excellence becomes the natural way of working, driving competitive advantage. Quality management is not just a technical discipline, it's a strategic competency that defines market leadership and organizational sustainability. As quality professionals, you are the architects of India's manufacturing future. Apply these principles to build world-class organizations that compete globally through quality excellence.